Yeah, but person.
Okay. Should I introduce myself?
No. This is Hal. He's going to talk about our own way to study groups.
He teaches archery.
He does.
Cool class.
What? Okay. This is the title of my talk. Since that's the title, and clearly I'm not going to mention any of my own work because that's the title. Okay. So now we study groups, and actually we study finite represented groups. So we've got a G and a finite representation of G. You all happy about this? Yeah, you know what that is? So the wrong way is to ask what can we learn about G by just looking at the representation. And here's a question we can ask. Given a word W and a GI, can we tell whether W represents the identity in the group? Okay, so the formal way to ask this question is this, the word problem. So it asks, is there an algorithm that takes as input one, a finite representation pi, right, something like that, and a word in GI, or W in GI, and decide spelling, and decide if W represents the identity in the group defined by pi. So that's the notation I use, that's the group defined by pi. Okay? So that's the question the word problem asks. So it turns out this question is too greedy. There's a theorem that says there exists a group, a finite represented group U such that this is unsolvable. The word problem is unsolvable. So if you only focus on this group U, you can't find algorithm. And the word problem is asking for a uniform algorithm that works for all presentation, all groups. Right? So this fails. The answer is no. Okay, so that's the word problem. Now you say, okay, I don't care about the word problem. Can I ask something else? Can I ask whether this group is abelian or free, things like that, or it's finite? So now let's ask that question. All right, so is there an algorithm? Algorithm. That takes the input. A finite representation. Pi. And decides if the group defined by pi is, say, finite or abelian. So there are a lot of words you can put in here, all right? So you can ask all these questions. And can you guess what the answer is? No, because that's the wrong way to study groups. So the answer is no, but the answer most of the time no. So now I'll explain what I mean by that most of the time. Alright, so this is definition. Markov property. All right. So a property P is called a Markov property. If it exists a finite, well, pair of finite groups, finite percentage groups. G plus, G minus, such that 1, G plus as P. Alright, and the second, if G minus embeds into H, and H is finitely percented, then H does not have P. Okay? In particular, G minus doesn't have P. Alright, so that's Markov property. Now, what are examples of Markov property? Any idea? Abelian, alright. So there is a finite percentage abelian group, and if you contain something non-abelian, then you must be non-abelian. What else?
Finite.
Finite. Okay. What else?
Solvable.
Solvable, very good. So solvable and then
Nope.
Nilpotent.
Hyperbolic.
Hyperbolic. Is that true?
No, you can't have a z squared in a hyperbolic group. So non-hyperbolic.
What if that subgroup is twisted inside a bigger group?
No.
So that's less obvious, but let's not do that.
Simple. Versatile.
And we should not mention anything in geometric group theory. Because of that title. What else? Free. Right, and what else? Torsion free. Oops. So it's a long list. You can find a lot of properties that are Markov.
Torsion.
Okay, so the big theorem is the answer is no for all these properties. Alright, so if P is a Markov property, and then there's no well, let's just do this. Then the answer to question 2 is no. such algorithm doesn't exist. All right, and I want to apologize because I'm going to prove this. So any questions so far? Is the statement clear? Does it make sense to apply, people?
Can you give us a simple property that
No, Marco?
it does have a yes answer question too?
No, actually. Yeah. In general, there's nothing you can tell about a group by just looking at it. Yeah. Presentation.
Finally presented.
Good. Okay. All right. I approve this. Do it. So approve. So let's say P is a Markov property. And that G plus and G minus be as in the definition of Markov property.
What's a group presentation? Just for reference.
What's a group presentation? So if you write something like this, let's do it easy. A, B, and then do something like this, a word and A, B. Okay? So this thing is a set of words. So this is a set of words, an A, B, right? So things like A, B, we know what that is. And mod by the equivalent relation generated by this, right? So this guy would be empty word, which we use that to denote, right? And if you got something like this, A, B, and using this, we can write this as BA. So this defines an equivalent relation between words, right? And then we mod this set by that equivalent relation. So that's another set, and then we define a group operation by concatenation of words, right? So that's well, you should ask that earlier. But I think you know this. You're just asking for the apply people.
I think he had a subtle technical point that he wasn't completely elucidating. But I think it's fine. They're all finely presented groups, so I don't think we have to worry about any subtleties.
Okay. G plus G minus are those two guys. So G plus has P and G minus doesn't have P. Alright. Now let U be a group, a finite presented group with unsolvable word problems. Okay, and we're going to construct the following. Review, construct. So like this, there's a set of finite presentations, W prime, for each W, word W in the generators of U. Okay. And such that if W equals 1 in U, then this thing is the group defined by pi W is isomorphic to G plus. Hence, it has SP, right? And so guess what I'm gonna write? If this is not 1, then this is isomorphic to G minus, hence doesn't have P. So we reduce the second question to the first question, and we know it's no to the first question, all right? Don't worry, the proof is easy.
These are if and only ifs, right?
Well, they're sort of, yeah. You can see from the second one that this is if only. Okay, now the worst part of this talk, technical lemma. So let K be a finite descending group. Right, it's 1 to n, R1 to Rm. Right. Any word W in Xi we define a group by finite representation LW. It looks like this. First put all the generators of K in there. And then we put 3 more, A, B, C. Alright? And then relations. All this. Now something ugly. Alright, something like this. That's the first type. Equals second type. And this is the commutator of W and P. Alright, so we know what that is. And this is C and last type is XIB, and this is for all I from 1 to n. Okay, so that's a finite representation, a bunch of equations and with just generators.
Is there anything we should be able to extract from it at this point by looking at it?
trying to force it to have unsolvable word problem by just tacking on message generators and relators?
No. Okay, I'm going to tell you what's going to happen. Right. So then, first, if this one is first, this one is if W equals 1 in K, right, if the word that I pick equals 1 in this group, then the whole thing collapses. And this is the identity group. Right, everything died. You can check this by. You should try to check this now. And if W is not 1, then K is a subgroup of LW by the obvious map. Right, you've got an obvious map that sends xi to xi.
This doesn't seem like it can be right.
Okay, so
Like-
W is 1, so you start with that, and
You start with
V
this.
cubed is C cubed, I
Did
guess.
I miss something?
yeah,
I think I missed something.
Yeah, there's got to be a W somewhere else. Because W, there's nothing special about W being 1 here. It just needs to commute with B, and you'll have the exact same relations.
Hmm.
W
Yeah, but
doesn't appear
W's
anywhere
not-
except in the
you
common
could
But
W.
it's no other
relations.
relations.
You
W
never
lives in
anywhere
there.
started W,
Yeah.
that any of the xi's were
That
going
what?
to commute with A, B, or C.
W lives in those,
Yeah.
and that's ABC. The only way for W to commute with B is W is trivial. Because there's no other relation that involves W.
There's no way of constructing it out of the 4 relations.
Okay.
Always hyperventilating.
Don't laugh too loud, but Andy's going to laugh.
Okay, I'll prove this at the end. And let's use that to prove the theorem. Right, so proof of the theorem. So here's the dilemma. So we know that U is a finite presented group with unsolvable problem. It's finitely presented. So it looks like that. And G plus is also finitely presented. G minus. Okay. Now, K is a free product of U and G minus. So if you don't know what free product is, here's the definition. Just put all the generators together. And then you put all the relations together. All right. Okay. Now since U has unsolvable word problem, K has unsolvable word problem. All right. What else is true? Also, by just looking at this, we know that, a property of free product. We know that U is a subgroup of K, and G minus is also a subgroup of K. Many chalk die. Can you guys see anything? It's hard to know.
Sarah's good where she is, right?
Sarah can see everything she wants to see.
Okay, so U is a subgroup of K, and any word W in yi's. So words in U let LW be as a lemma. Alright, so that crazy guy. Now we let pi W to be the free product of LW and G plus. Okay. Now by the lemma, if W equals 1 in K, if W equals 1 in U, hence W equals 1 in K, then what is true? Oh, sorry. When it's not 1, then we know that K is embedded in LW. Let's just use that. And what is inside K?
And it's just U that's in LW.
No, he's using that K to build all them. He's just starting with the word he happens to know is in U inside of K.
Okay.
U is inside K, K is inside that, and this guy is inside IW. Okay. Then what? Then what do we know? Actually, I don't care about you. Sorry.
You don't care about you.
I don't care about you exactly. I'm using this fact here. The G minus is in K. So now what can we say about that guy? It contains G minus.
Does not have property.
So this has it's now now if W is 1 in U, hence W is 1 in K, then what happened? Then this whole group collapsed to identity. So pi W is just identity free product with G plus. Okay? Hence SP. Okay? So we got what we want. We just reduced the second question to the first question. So we know the answer is no. So now we only have to prove this lamp. And it's not that bad. What time is it?
12:45, 46.
Wow. It's going to be a very short talk.
That's okay.
Okay, let's prove this. The first part is easy. Right? So if W is 1, let's look at 3. What we have? We have 3. So if W is 1, then the commutator of W and B is also 1. Okay, so this guy is 1 equals to that guy. So it tells you that B is also
BQ.
1.
DQ.
DQ.
Huh. Apparently it should be B. Sorry,
Okay.
but I never used that fact before. So. Okay, so B is 1. And once you know B is 1, you use the first one. These two together will tell you
C.
C is 1. And then now you use that together with 2, and you know that A is 1.
Now 4.
So A, B, C, they're all 1. Now we use the last one to see that yeah, they're all 1. And 4. Next side, they're all 1. Alright, so the whole group is 1. Okay, so that's the easy part. And let's prove the hard part. And we'll be done. So we look at this group. It's K star with sorry, let's just do this first. 3 groups generated by B and C, right? 2 generated, no relation. And then we consider the subgroup of this group, C, generated by a bunch of words, generated by B, and everything on the right hand side of these equations. Alright, so shall I write this down? And the last one. From 1 to n. Alright. So what can we say about this group? Claim is C is 3. Of course, it's a subgroup of a free group of rank 1, 2, 3, 4, and then you got n here. Alright. With all this, let's call this set, let's call this set P sub C being a free generating set. Is that clear? The point is that if you multiply all this guy together, you won't get identity. I mean, you multiply the powers of this, any power of these guys, inverses. Because all these guys, they're wearing very thick clothes. They're conjugate of C by things. And they don't cancel out. Okay. So you can sit down and try to do the computation. It's not hard to see that you can get cancellations. Okay. So since there's no relation between these guys, they must generate a free group. So the rank is that, and that's free. What else? The second part. at this guy, K free product with AB, the free group generated by AB, and think about a subgroup A generated by, I think that's what I'm going to write down, B, and together with everything on the left hand side of this equation, all this guy. All right. So we'll write this down. A. Last guy is that. XIB. Okay. So again, we can say the same thing about this subgroup. This subgroup is claim is that A is free of rank n plus 4.
How can A be free when K has relations R1 to Rn?
The point is, these guys, they don't have relation between them. For the same reason.
The exercise don't get
Because this guy doesn't die. Okay? So it's free of rank that. So they're isomorphic. A and C, they're isomorphic. Now you got two groups, this guy and that guy. And they're isomorphic subgroups. So you want to do, what do you want to do?
Amalgamated product.
Amalgamated free product. So we just form this. And that's the other guy. Right? So when you form amalgamated free product, what is this group? So what you do is you identify B with B, and the first guy with the first guy, second guy with the second guy. The relation you get, they are just all this. And then together with the relation of K. So the guy you get is just this guy. Okay, now we're done, almost. What do we want to show? We want to show that K is a subgroup of this guy, right? But this is a free product. So K is a subgroup of this guy. And then the fundamental theorem about amalgamated free product is that it tells you that this is a subgroup. This piece is a subgroup of the whole thing. So this embeds into the whole thing. Okay, we're done. So to sum up, a wrong way to study groups is by computation. Sorry, five people, sorry. It's just wrong. So what is the right way? Well, not the right way. What is a right way to study groups?
Small cancellation.
That's an answer. Right way to study groups. And you know what I'm going to say?
Combinatorially.
Geometrical theory. All right.
So you just proved that computational group theory is wrong?
No, that's a joke. So that's it. Right.
Any questions?
Oh, wow.
Slow second. Well, you is you. Oh, were you in the middle?
Oh,
Is it
pain.
Is it Graham?
Okay, write it down. It's finally presented.
What person is associated with it?
Nova Carpenter.
Yeah, I didn't mention name because of the title.
Okay. It's not,
Some Russian.
the
No,
one,
no,
the
the
one,
card.
the H and H and M.
Or the names used.
No, not the Neumann, it's the other guy from the 50s.
Hingman?
Yeah, Hibben.
Yeah.
Okay.
I don't study the dark side of computing.
I think what you do really is you start with a Turing machine, you make it into a semi-group, then you do some clever things to make the semi-group into a group, and it's a very ugly group.
I know Hickman made one that didn't have, that had a finally generated group that had a non-recursively presented presentation that had an unsolvable word problem. But somebody else did
Embed
it
that into it.
finite, finally presented.
I think you can embed that group into a finite percent group.
Okay.
Something like a PDF.
Okay.
So if you don't like looking at group theory by computations, why do you care about equation problems?
See, once
Yeah,
you
so I'm
walk around the
changing.
daily graph.
Okay.
Yeah.
That's
just a
show them
joke.
how wrong they are.
Because there are things you can compute, yeah.
Okay.
But you don't want to compute them by computation.
Right.
Do you have a question, Andy?
What's your favorite math book?
I don't have one.
What's your least favorite math book?
Highest 3.
Least, I don't want to answer that question.
You're in America. No one can make you answer that.
You can plead with it.
Okay.
All right.
Thanks.
Thank you.